So I've just shown you 4 different measures of center, and you may be wondering, like, well, why not just pick the best one and just go with that? Why do I need to present all these different measures of center? And believe me, I've actually skipped some. The idea is they all have their own unique, like, good thing about them. And so that'll be the point of this video, is just kind of tell you, like, why do we need so many measures and what's so good about these things. So first off, I want to talk about something called reliability in statistics. Now, if you ever look that up on Wikipedia, well, I'm just telling you, don't, because the actual definition of reliability is horribly complicated. But here's the gist of it. A reliable measure is going to kind of imply some consistency from sample to sample. In other words, if I do an experiment in my laboratory and you do your experiment in your laboratory, our measures of center are going to be really close to each other. Or if I go take a sample of 30 students to find out their average age and you go do the same thing, our average, if it's reliable, should be really close to each other. And that's really actually the advantage of the mean. So the mean is reliable, and specifically the reason why measures are reliable is because they're close to the population version of that measure of center. Now, a mid-range, a mode, a median, those are not going to be as reliable. In other words, it's possible that just due to the random nature of gathering data, my sample median may not be that close to your sample median, or at least I would expect our sample means to be closer to each other because they're closer to the actual population mean. So I've got a quick example here of rolling a D20 die, right? So I just rolled it 5 times and then just found our simple measures of center, right? So we can immediately see with the mode, oh, this is a problem. Like sometimes it'll be a number, sometimes it won't even exist, right? So this idea of reliable is just completely out the door. And as I look at comparing the numbers across here, because I really did, like literally I rolled a die. I just didn't want to make that part of the video because it's boring to watch me roll a die 10 times. But I literally, this is completely random data. And we see these means of 8 and 9 are only 1 apart. The medians are 2 apart, and the mid-range is 2.5 apart. And that's actually essentially the order I'd expect things to be. The mean is the most reliable of these, and the median is a little bit behind it. So that's the first thing, is reliability. Here's where that becomes really useful to be reliable, is when I'm actually trying to make an estimate for the whole population. Right? So if I'm trying to, let's say, estimate when people start smoking. Now, the mean is a little bit hard to interpret because it's, you know, that balancing point or the communist measure of when we even everyone's age out. Like, it's hard to interpret in that sense. But I can be more sure that my sample mean is going to be close to the actual true mean of all smokers if I look at a mean instead of a median, right? The median age when people start smoking is maybe easier to interpret because, you know, half of the people would be less than that and half would be more. But I might be missing, or my sample, just the data that I gathered, might be considerably off from where the true population lies, or true population median lies. So that's the advantage of a reliable measure, is that it's great for inferential statistics. Remember, that's when we take what we found in our sample and we extrapolate that to talk about the entire population. So the mean is going to be great for inferential statistics when we're trying to talk about the whole population because it's reliable. These words reliable and consistent have very formal mathematical definitions of statistics that I'm not going to care about. It's just this kind of idea of we'll consistently get numbers that are pretty close to each other when we have reliable measures. Another issue we might be concerned with is outliers. Okay, so when I'm finding a balancing point, and I've got, like, let's say a bunch of numbers down here, let's say their incomes, a bunch of people with low incomes, and then a super high income. That high income, as I'm talking about a balancing point, is going to move that balancing point over here, which is now far away from where my typical values were, and then far below still this extreme outlier of super high income. So I need to be concerned with what actually happens with outliers or extreme values. And are they skewing things away from where they should really be in order for me to interpret a center correctly? So let's talk about those outliers. So remember when we have right skewed data, that tends to make high outliers. Left skewed data tends to generate low outliers. And remember, outliers are just values that are far away from the other values, not like it's garbage data that we got to get rid of or misleading data. Sometimes it's actually very informative data. So what we want with outliers typically is what's called a resistant measure. So a resistant measure is one that doesn't change very much due to adding in outliers or taking out outliers. They're going to stay kind of in a similar place. The contrast to that would be sensitive measures. So sensitive measures are completely the opposite. They move by a very large amount due to the presence of outliers. Okay, so let's look at this resistant example I've got here. So I was thinking of, if you live here in Casper, you maybe know the McMurray Mansion right next to McMurray Park. So that whole neighborhood's, got nice houses, but there's one like super mega mansion also. Okay, so let's say we're trying to find the average home value in that neighborhood. Well, if I've got just a kind of a random sample of home prices in the thousands, right? And we'll just guess. I honestly have no idea how to guess at, enormous mega mansion home prices, but let's just say it's $10 million. I don't know. Well, that means I've got a bunch of houses that are in the $300,000 to $500,000 range, and then a $10 million house. So as I look at the mean, I'm at almost $2 million, which honestly doesn't represent any of the homes in that neighborhood, right? None of them are near that value. They're either way below that or way above it. But with the median of 420,000, which is actually pretty typical for the neighborhood. And again, let's say I do another sample where I don't happen to get that one outlier in the neighborhood. Well, now I've got a mean that's a little bit closer to the middle and a median that kind of stays the same. Well, look at how far apart these means are. That's insane, right? In other words, going from one sample that had an outlier to a sample that didn't have an outlier changes where that mean is by a huge amount. That's a sensitive measure. I tend to not want those because it's going to end up giving me kind of a skewed understanding, right? That $2 million or $1.78 million mean was completely pointless for that neighborhood. It doesn't tell me anything about the neighborhood because none of the homes were close to that value. So what I'm going to want generally with that outlier or highly skewed, right, left skewed or right skewed data is going to be a resistant measure, which is the median, right? So the median is going to be the most resistant measure. And if we think about things the other way, the most sensitive, if you think about it, what is by definition an outlier going to be? A minimum or a maximum, right? If it's a high outlier, it'll be a maximum for the data set. If it's a low outlier, it'll be the minimum value for the data set. Those are the only two numbers that we have in a mid-range. So mid-range is going to be extremely sensitive, and that's going to tend to be something that I don't want. So just to kind of recap what I've got here, the mean is very reliable. It's going to be fantastically useful when we do inferential statistics. The median is very resistant, so I'm going to really want to use that when I've got outlier or skewed data that's where I really want that measure to represent my data rather than just the unusual values. And I'm going to tend to want to avoid sensitive measures whenever I've got that kind of situation, which unfortunately the mean is, and definitely the mid-range. In the next video, I'll talk about how we should pick which one of these measures to use.